We showed previously that during beta decay, energy is released. However, careful experiments showed that most beta particles do not have enough kinetic energy to account for all the energy released. This raised an interesting question. If the beta particle only carried away part of the energy, where did the rest of the energy go? This question was finally answered in 1930, when Wolfgang Pauli proposed that part of the energy is carried away by another particle that is emitted along with the beta particle. This additional particle is called the neutrino, and its existence was verified experimentally in 1956. The Greek letter nu is used to symbolize the neutrino. The beta-minus decay of the thorium-234 that we looked at earlier is more correctly written in the following way, where thorium-234 decays into a protactinium-234 atom plus an electron plus an antineutrino. The bar above the nu is included to indicate that the neutrino emitted in this particular decay process is the antimatter neutrino or antineutrino. A normal neutrino, a nu without the bar, is emitted when beta plus decay occurs. The emission of neutrinos and beta particles involves a force called the weak nuclear force, because it is much weaker than the strong nuclear force. It is now known that the weak nuclear force and the electromagnetic force are two different manifestations of a single, more fundamental force called the electroweak force. The electroweak force, the gravitational force, and the strong nuclear force make up the three fundamental forces in nature. The neutrino has zero electric charge and is extremely difficult to detect because it interacts very weakly with matter. For example, the average neutrino can penetrate 1 light year of lead, approximately 9.5 times 10 to the 15 meters, without interacting with it at all. Thus, even though trillions of neutrinos pass through your body every second, they have no effect. One of the major scientific questions of our time is whether neutrinos have mass. The question is important because neutrinos are so plentiful in the universe. Even a very small mass could account for a significant portion of the mass in the universe and possibly could have an effect on the formation of galaxies. In 1998, a very sensitive experiment yielded the first strong but indirect evidence that neutrinos do indeed have a small mass. Just for comparison, the mass of the electron neutrino is less than 0.0004% of the mass of an electron. This finding implies that neutrinos travel at less than the speed of light, because if the neutrino's mass were zero, like that of a photon, it would indeed travel at the speed of light.